Okay. So after going through some of the challenges and opportunities and the bigger theme of a modern embedded system, we'll start taking the system layer by layer, starting from software programming and then sensors, actuators, IOs, multi-cores, and all that stuff, and then discuss how we can address these challenges, right, from a technical perspective. So the reason I started by embedded software is because this is what you'll be doing in all the labs. Starting from lab 1, you will be really writing software to control the embedded system, and you'll be doing this in C, right? So why it's good to really revisit some of the software development techniques and aspects for an embedded system. Now, I know that you have already taken programming courses, including C and C++ and all that stuff. So hopefully that's not new to you. Also in 241, you did really program, I think, BIC using assembly and C or only assembly and C, right? You did this as well. But it's always important to think about if I have already taken a programming course. The programming course was intended more towards a general purpose system, right? Now, is there any difference when I move from a general purpose system to an embedded system? Right? So are there some considerations that I should maybe care about more, right? And as we will see in today's lecture, there are many considerations you have to put in mind when you are writing programs for embedded systems that usually you don't care about when you really write programs for general purpose systems, right? Good. So the first one is what we call a programming model, right? I think in your general programming course in second year, well, you have an IDE in your laptop, you write source code, you compile it, and then you run the binary and see it out, right? What is really happening there is your target platform is the same platform that you are using for development, right? So it's just the same laptop. Now in 241, that's not the case. In 241, if you remember correctly, you used an IDE in a desktop or laptop, right? And then you write your program, you compile it, you obtain a hex file, right? Which is your binary code, and then what do? You load it to the embedded system, right? Which means your target platform is different from the platform that you use for development. First of all, why that's the case? Why this was needed? Did you ever ask why should just go through this hassle? Why I really don't do whatever we did in our normal programming course when my target platform is the same as the host platform? Yeah. Yeah, but wouldn't it be more portable if I just really have the embedded system and write the software directly into it?
Not for not portability, like making it more lightweight.
Yeah, you're in the right track, which basically, yeah.
But we can simulate the code before implementing it on the system.
An excellent point. And why we cannot really simulate it if we are developing an embedded system? Because of the critical constraint. Yeah, all the three are really saying the same thing. So the key idea is the embedded system is very resource constrained. It does not allow you to run like a GUI IDE that you can simulate stuff and look into the result and then burn it there, right? It will only take the bare metal application binary and execute it for you. So you need something that you can play around with, try different things, simulate, target different embedded platforms. And then once you are done testing and development, you just go and burn it there, right? So we call this the host target model for programming, right? You are using the host for development that is different than your eventual target, right? Now, to enable this, your laptop is mostly an Intel machine or AMD machine, so it's an x86, like ISA, right? Like in the first lecture, we talked about instruction setup. Your platform, well, in 241, it was a BIC, which is definitely a RISC microarchitecture. These days, it's an ARM, right, which is also a RISC micro. So it's a different ISA. Can I really write a program for an ISA and then target a different ISA? This is a little bit against what we said in lecture 0, right? Is that the compiler should be aware of the eventual ISA that you are targeting. So how, in fact, this was possible? Do you ever think of that?
The compiler, the IDE we use has the ISA for the
for the target machine. So it's asking you what is your target machine, and they do a process called cross compilation. right? So in the background, there is a very complex process that the compiler is doing for you through the IDE. So what this says, okay, right now I'm going to execute and simulate this code in an x86 machine. But at the end, when I create the hex file, the assembly, and the binary, I'm going to create it for an ARM machine, for example, right? This is called cross compilation, right? Without cross compilation, we couldn't in fact do any of this because you cannot really write software in a machine and you're targeting a different machine unless it's the same IC. Good. These are some of the challenges that comes to embedded systems that you never think about when you talk about a general purpose system. Right? So if you move to a more powerful embedded system, something like a Raspberry Pi or an NVIDIA Nano GPU or system on a chip, well, this enables you really to develop on the same platform, right? So we call this the standalone model, where your host and target is the same, pretty much the same as the general purpose system, right? Why? Because in Raspberry Pi, for instance, you have an operating system, Raspbian, that really hook it up into a monitor and then write your development and testing and everything on the same platform, right? So again, this wasn't possible in, for example, our nuclear board because, well, it's not as powerful as a Raspberry Pi, right? It cannot really enable you to run this IDE. Okay. Some of the other, maybe we should discuss this a little bit before you look into the slide. So there are some other few challenges when it comes to an embedded system. So let's try to reflect on the differences between embedded systems and general purpose systems that we had in the previous two lectures, and think of how does this really impact programming if you write programs for an embedded system. What are some of the things that will come to your mind where, well, I should be aware of what I'm really doing for an embedded system because of few characteristics for an embedded system?
Programs really need to be optimized. I cannot have million lines of code in an embedded system.
Excellent.
To do the same task, but with much less lines of code.
Yeah, excellent. And the reason for this is an embedded system.
Memory space.
Yeah, memory space, usually resource constrained, right? So we call embedded systems resource constrained devices compared to your laptop, for example, or desktop. So you have to be aware of the resource, right? And we will see some of the implications, how you pick up your data types, how you really define your memory behavior, that stuff, right? So that's one of the things to keep in mind, which is the most important one, by the way. So thank you. So some other is in an embedded system, you in fact most of the time have a lower access to the hardware, right? So if you look into your big programming experience for 241, you're interacting directly with the hardware, right? So some of the times, for example, to enable an interrupt or to enable a GPIO, you go to a particular register in the memory, right? And then mask a certain bit to make it like an input port or an output port, right? But if you think about this low-level programmability, you will never be able to do this in your laptop. In your laptop, you will never say, I want to access the register that is really controlling my mouse input port and then turn it out to be output. That's not there, right? You would always have layers of libraries and firmware and things that are really built for you, right? So in an embedded system, well, in your past experience, there was no even an operating system. Your program was directly interacting with the hardware, right? And interacting with the hardware at the bit level, right? So this low-level control of an embedded system is one of the features of an embedded system programming compared to a general purpose program. How this is really important or how does it really impact an embedded system engineer, we will also discuss this. The third thing is, compared to general purpose systems, where in fact all the system on a chip or processors more or less kind of converge to few options, either it's like like an ARM mobile application programming, or your laptops and desktops are mostly x86 machines, whether they are AMD or Intel. In embedded, there are so many companies, so many platforms, right? Last time we said ARM is the dominant, that's true. But even with ARM is not really a manufacturing company. They are a licensed company. Like they give companies the cores, and then the companies the SoCs. For example, the board we are using in this lab, from which company it is? You know?
From
Like the 14411? ST Microelectronics, right? That's one of the companies manufacturing chips for embedded systems. I think in last lecture or the lecture before, we had a video from Texas Instruments, right? There's also NXP. There are Infineon, many companies that are building hardware for embedded systems, and each company has its own SoC, IDE, way of writing software, way of laying down the memory in the what we call a memory mapping. So this diversity on the market, which is not the case for general purpose systems, makes it very hard to really write a portable code, because the code that runs for your ID in BEC is different than, well, BEC is different IC, so it's a harder example. But even in your second year, if you had a different, like an ARM core, but a different platform than the ST microelectronics, like another Texas Instrument board, for example, your ID will be different. The way you write code will be slightly different, right? So it's very hard to really develop something that is standardized in an embedded system, right? Now, when it comes to a programming language, one of the differences for an embedded system compared to a general purpose system, but there are so many high-level programming languages for general purpose systems. What is the most famous one? Python nowadays, yeah. Well, every 10 years maybe you have a different language, right? But C also is very common, right? C++, Java, JavaScript, C#, whatever language. There's so many languages, right? But what about embedded systems? They are mostly C, right? So what is the reason? Very fast, yeah, very efficient, and gives you the low access control. We'll have a few of these discussions here. But one of the differences is many programming languages in general purpose systems, there are very few in embedded, and they are mostly C, right? Like most of the embedded systems are in fact programmed using C. Well, I think for you, I updated this thing. I'm opening an old slide because this is the programming course I used to teach before. Basically, I was trying to make the link between what you guys have covered in earlier courses and what we do in this course. Simply, or ignore this code for now. It's more of your programming course. What is the code for your programming course? The C1?
C, 241, I think.
241?
I think.
No, 241 was the embedded interfacing one, right?
Like C++.
Yeah, that, oh, C++.
So you mean the one for microcontroller?
No, the one for like C++, the general program.
Oh, okay, 120.
120, okay, yeah. So simply C is a very old language. It's from 70, right? But the point is that it's still surviving up until now. It's one of the oldest, right? So why C is still surviving, even in general purpose systems? Why everything is building on C? That's a very excellent point.
It's fast.
Very, very fast, very performant, right? Like someone can say, some of you said Python is the most common, right? But if you, Python is now very common because of libraries and machine learning. If you look into all the machine learning frameworks right now, PyTorch or TensorFlow, name it, they are in fact written in, not in Python. They are written in C, right? Look, the Python is the interfacing one for you, right? What about operating systems? They're mostly C, right? That's also because of performance, right? So C is a very, very efficient language, right? This is why it's still surviving up until the moment. There is a very nice video here. I also added on your iLearn. Some of you might not know Linus, but Linus is in fact the inventor. I don't know if inventor is the right word for C, but he is simply the one with the C standardization, right? Do you know what else did you do? Did you get that term before?
Yes.
Linux, right? It's coming from the name, right? Linux. Something else? Git. Yeah, excellent. Thank you. So this guy basically alone came up with C, Linux, and Git, right? Like I think this is more like a legion for computing system, right? He has a very nice video here, interview. There is, well, the title, I can tell what he's going to say in the video from the title. Nothing is better than C, right? He's a very active caller for that C is in fact the best language up until now, right? It's very nice C. So I think you should hopefully watch this video. Just broaden your mind about how people think about different languages. So we said it's really fast, efficient, and portable. Something for embedded systems, especially. We said embedded systems usually give you a lower access to the hardware, right? Well, naturally it comes to C. Like C is the closest high-level programming language to assembly, right? First of all, what is really the closest to the machine? It's the machine code, right? Like machines don't really understand Java or Python or C or anything, just zeros and ones. What is above machine code? Assembly. That's the closest, right? In the past, well, when I was in my undergrad, I wrote my graduation project fully in assembly. It was like hundreds of code. It's a very, very tedious task, right? Not very human, but kind of natural way to do things and very, very slow to develop, right? But assembly is the closest to machine code. Now, if you look into all the high-level languages compared to assembly, the closest one to assembly is C, right? So C is the closest language that gives you control to the hardware, to the level that, in fact, in C, you can write assembly code. You can embed assembly inside C. Good. So naturally, C is more, more natural to use it for embedded because you need a hardware control, low-level hardware control, and C gives you this. And then an example of this close to machine thing is pointers. You guys have pointers, I think, in your yeah. So now in pointers, an aspect of C that does not exist in any other language, and it's in C++ because of C, but it does not exist in Java or Python or anything else, is you can directly access memory addresses using variables, right? So you can control memory manually as a programmer and allocate it and deallocate it, what we call dynamic memory allocation. There is no other language that can give you this, right? Someone can say, did you guys take Java? Any means?
Yeah.
Yeah, I mean, there is basically a fallacy that says, well, references in Java are the same as pointers in C. Do you know references in Java? Good, because in last class, like someone said, references, they exist in Java, right? So simply just the pointers allows you to address a particular address in there, right? Like I go there and write, I want to access location 0xFF3F, for example, right? Which is the register of the GPIO for, I mean, our port A, for example, in the controller, right? No other language enables you to do this. So that's a very big advantage. What is the disadvantage?
It's hard.
Very hard to code and also susceptible to human errors, right? In C, there is no garbage collector. So I need to allocate memory myself through pointers, but you also need to deallocate them. Otherwise, you'll have memory overflow and memory issues, right? Memory leaking. For this reason, as we'll see towards the end of the lecture, this next time, that in reality, most safety critical systems disallow by the certification to use any pointer or dynamic memory allocation, including software for automotive, for example. Which means if you are a software engineer, like embedded software engineer for automotive, following the AUTOSAR standard, I cannot write pointers. You cannot dynamically allocate memory. The reason is they are unsafe because they are susceptible to memory overflow, security vulnerabilities, and memory issues. Good. So these are some of the problems we just discussed right now. They are unsafe, enables leaking and undefined behavior, and you need a manual control of the dynamic. How much time do we have left? So I see you guys are. Yeah, we still have some time. Okay, so few slides that simply, yeah.
Yes, suppose you said dynamic memory allocation is not really used in what sense?
Not allowed in the high safety critical systems.
Okay.
Up until now, the standard disallows them, right? It tells you that your memory usage must be static, right? Is to have a defined behavior. Some of the things we said, I need a low-level hardware control, which means I need to access certain bits and certain registers. So you need to review really how we handle things. So as an embedded system engineer, you need to be aware of the type, like numbering systems who are mainly in binary. You need to access particular bits. We use a feature called bitwise manipulation a lot in embedded, right? To control certain bits in a register through masking. So this is like a few of these slides, I only have them there so that you have them when you study. Like you just refresh your mind about numbering systems, data types, and all that stuff. Now, data types in C, why it's important to review in embedded? Because your friend said I need to be very well optimized for memory, right? So assume, for example, I want to access certain bits in a register that I know there always will only be 8 bits. It doesn't make any sense that you define a variable that is an int, right? Because your int can be 32-bit. But you're only going to use 8 bits. So you're wasting, how many bits? 24 bits for no reason, right? 75% of your memory is wasted for this variable for no reason, right? So you need to be very aware of how you define your variables and types in embedded, right, from B to C. Yeah, so if there is something that can really work for example, for a character or an integer, you don't go ahead and define a double, right? I used to teach a programming course for our students in MathMaster. It was first year programming course. In a general programming, it's always good also to talk about these things, how to be efficient in memory, how to be efficient in hardware. But in general purpose programming, people usually don't really care. They only care about the functionality. You have a very powerful machine anyway. So if you allocated 1 kilobyte more, nobody cares, right? But if you talk about an embedded system where your whole memory can be an 8 kilobyte memory, if you waste 1 kilobyte of memory in your application, that's very, very inefficient, right? So 1 kilobyte out of 8 is different than 1 kilobyte out of 4 gigs. Good. For example, if you're doing an embedded system engineer interview and they ask you to write a piece of a program, and then, well, the only thing you know about C is your general purpose C++ course. You define everything as a double. You'll never succeed in this, right? Because you're not very efficient. Everything is 64-bit. You only have like a very small memory. You define 10 variables, you run out of memory. Your program will not run. Good. More than this, it's not only about data types, but also modifiers of the data types. So it's not only about defining a character, for example, because a character is 8 bits. But what if, for example, you are indexing a register? Generally, a character that is 8-bit allows both for signed and unsigned values, right? So if you have 8 bits, you go simply from negative 128 to a positive 127, right? But if you're indexing a register, you will never expect an index to be a negative, right? So it's more efficient to really have all your 8 bits dedicated to be positive numbers to enable a higher range. How do we do this?
That's
Unsigned, right? So defining an unsigned character allows you, using the exact same number of bits in the memory, to go from 0 to 255, right? So you doubled your range for your indexing without losing any extra bit in the memory, right? Using modifiers. Okay? This is why you will find very common in C, people are not really writing using any of these types. What they do is UN8, UN16, UN32, right? Unsigned and 8, unsigned 8. So they put in the type, the width of the memory, right? Good. If I give you, for example, in a midterm or a final exam, and ask you to write a small piece of software, and then it requires you to write a UN8, but then you define a double, know that there is a problem with your code. Right? Okay, good. Just a few examples, things. Something you should also know about what C allows and does not allow, like some undefined behavior in some of the variables. Yeah, maybe another note here about the types. So for example, an int, we usually say an int goes from 16 to 64-bit. Why an int has a variable width? Because it depends on the machine that you are targeting, right? Most of our modern machines, do you know how many, like what is the width of the registers in the laptops? 64, right? 32 with the old ones. I don't think any of you owned like a 32-bit machine. I used to have a 32-bit machine like 12 years ago, right? But most of all the modern laptops, desktops, since maybe 10 years ago, are 64 bits, right? What about embedded systems? Do you know what was the width of your big chip in 241?
16 or 24, I don't think.
Okay, so what about Arduino? The smallest Arduino, which is the only one, is 8 bits, right? It's an 8-bit machine. So what does it mean? We call this the machine width. It means that all the registers in this chip is 8 bits, right? Well, there are 16-bit Arduinos, there are 32-bit Arduinos. What about the ESP32? 32 from the name, right? It's called the ESP32 because it has 32-bit registers. What about our device, like the Nucleo RGB board? It's a 64-bit ARM tools, which means it's like a lot, right, for an embedded system. It's one of the higher performance ones. Good. So why is good to know these things? Because, for example, in the C standard, the width of an integer is in fact defined by the machine width, right? So if you really define something like int(x) and you put in a number and you try to execute this on ESP32 or an Arduino or in our ST device, then you will have a different width, right? Because the integer is variable based on the machine. People in embedded systems, and in fact, again, we'll see in the next lecture that the standard for safety critical systems, what we call the ANSI, forces you not to use a variable int width. You must really put the width in the type. Why? To be deterministic, to be independent of the target machine. You have to tell me I'm using an int8 or an int16 or an int32 to make sure that your software always has a deterministic behavior. Okay? Good. I think we can stop here because otherwise I have a long example that will not be able to. Yeah, we have 1 minute. So let's stop here. We don't have a lecture on Thursday. Okay, so we'll continue this topic on next Tuesday. See you next.